look a little different here. Evidently, I didn't redo these last year, so I don't know why, but this will work. And I don't know, because this is from the old book, I don't know if these examples perfectly match the examples in your book. So if they don't, sorry, but they basically walk you through the same thing, okay? So far, we've talked about weak acids and what happens when you put them in water, and weak bases when you put them in water, and then salt solutions and what happens when you put them in water, right? Because the salt dissociates, and then it has some sort of either acidic or basic effect on the solution. This unit has traditionally been one of the toughest ones out of the entire year, because what happens is we take a bunch of concepts and we just throw them all together. So now what you're getting is what happens if I add a weak acid and a weak base at the same time. Then what does that do to the pH, right? So far, all we've really done is what happens when I put in a weak acid. So you've got the weak acid and its conjugate base, but what if I throw something else in there, okay? So that's not really what we're going to talk about here. What we're going to talk about here is just what happens when I throw in a common ion, all right, and what effect does that have. So this I think will make sense. So let's say that we just dump we've got a solution that has acetic acid in it, and then we put some sodium acetate into that solution. And we want to know what's going to happen to the pH of the solution, okay? So what I want to do here is basically write an equation that will help me kind of think through this. Now, is this the example in the book? Yeah. Okay. I don't know if this was out of the book or if I just made this up so I could talk about it. I don't remember. But anyway, so I want to write an equation that will help me kind of think about this. So let's say that we start just with the solution of acetic acid, right? So we've got this HC2H3O2. And when I put that into water, it's going to dissociate. You can write that one of two ways. You can write it with the water and then have H3O plus on the other side. Or you can just, shortcut it and write the H plus and the C2H3O2 minus, like this, okay? Either way will work fine for our purposes. So that's your equilibrium that you've got going on in your solution of acetic acid, okay? So then you're going to add NaC2H3O2. All right, now as soon as you add, this is an ionic compound, sodium acetate, because it's a cation and a polyatomic anion, right? So plus and a minus. So as soon as you put that in water, it's going to dissociate, right? Now how do I know this one's going to dissociate for sure? An ionic compound, how do I know it's going to dissolve? It has something to do with the sodium. Does sodium ever precipitate with anything ever? Okay, so I know for sure that this is going to split apart into its ions, all right? So those are the two ions I have in solution. Well, we already said, well, okay, I shouldn't say that, okay? But is there any Na plus anywhere in this other equilibrium? So I'm kind of just dumping an ion in there that doesn't do anything to the acetic acid, right? So we can forget about the sodium. But notice this. I have just dumped in something that is a product in this equilibrium, right? So thinking about Le Chatelier, if I add something that's a product, which way is that going to push the equilibrium? It's going to push it towards the reactants, right? And push it back this way, which means that we're going to make more of the acetic acid, okay? So then what's going to happen to the concentration of H plus if I put in this sodium acetate? What's going to happen to this right here? It's going to increase? Well, it'd either be increase or decrease, right? I mean, those are your two possibilities. Okay, so I'm putting more of the C2H3O2 minus in, right? So now that's going to start reacting with the H plus to make more of this. So the H plus concentration is actually going to decrease over time. Does that make sense? Because we're pouring more of this in, but we're not adding any of the H plus. Okay? So the H plus is going to decrease, which does what to the pH? Say it again. Okay, so then the pH would increase, right? Because the more H plus you have, the lower the pH is going to go, the more acidic it will be. Okay? So if we're removing H plus from the system, or H3O plus, depending on, I guess I was thinking in terms of this equilibrium because I asked about the H plus. But if you remove that H plus from the system, now you have less H plus, which is going to make your pH higher. Okay? So you can actually lower the pH of this system by dumping in sodium acetate. Now, the other reason that kind of makes sense is because sodium acetate is a weak base, right? Because the acetate is an anion that's probably going to grab hydrogens and, act like a base. So it kind of makes sense that would raise the pH of the solution a little bit. Okay? All right. So this is known as the common ion effect. If you've got a weak electrolyte, it will ionize less if a strong electrolyte is added into the solution that has an ion in common with the weak electrolyte. Kind of long and drawn out. But what that basically means, so the weak electrolyte in our last example is the acetic acid, the HC2H3O2. That's a weak electrolyte because it doesn't dissociate all that much in water. Okay? So we've got an equilibrium that's happening here. Okay? And it says that weak electrolyte will ionize less if a strong electrolyte is added into the solution. Our strong electrolyte over here, whoops, went the wrong way, sorry. Our strong electrolyte is the sodium acetate because that's going to completely dissociate, right? And it has an ion in common, which it does right here, the acetate ion. Then it pushes this equilibrium back towards the left so that this acetic acid ionizes less. Okay, in other words, there's less of the H plus when we get done because this is splitting apart less than it was before. Okay? So that's the common ion effect. So here's a problem that kind of deals with that. Let's say we've got 0.30 moles of acetic acid and 0.30 moles of sodium acetate, and we've got 1 liter of solution. Okay? So really, this is not all that different from the problems that we've been doing, except there's just kind of one added thing that you have to watch out for. Okay? So the first thing I'm going to do, I want to know the pH of the solution. So what does that mean that I ultimately have to calculate here? The H plus concentration, right? So I've got 2 possible equilibrium equations that I could write here. I could write the one for acetic acid, or I could write the one for acetate, right? One of those is going to give me H plus, the other one is not. So I think I'd rather use the one that gives me H plus just because it's going to be a little bit easier to work with. Does that make sense? I can work from either of these, okay? But which one is going to give me H plus in the reaction itself, in the equation? The acid or the base? Yes, that's right. It's the acid. See, I can pretend that you guys are answering and no one will ever know. Except for I just said that, so now people will know. But okay, so if I write the equilibrium equation for the acid, acetic acid, then H plus is part of the equation, right? And so is the C2H3O2 minus, the acetate ion. So we've got our bases covered here, all right? So then I'm going to make an ice table. Now, one thing I am going to need to look up is the Ka for acetic acid, which I don't remember off the top of my head. Tell you what, while I'm explaining this, could one of you guys look up the Ka for acetic acid? It might be. Is that the example in the book?
It says 1.8 times 10 to the negative 8.
Okay, thank you. Okay, 1.8 times 10 to the negative fifth is our Ka, so that's going to help. All right, so in our ice table, what's the initial concentration of the acetic acid? .3, right? Because it's 0.3 moles in 1 liter, so it's 0.30. What's the initial concentration of our H plus? 0. What's the initial concentration of our C2H3O2 minus? Normally, it would be 0, right? In the last unit, what we did, we put 0 on those two. But we have some sodium acetate in that solution as well, right? So we actually have a beginning concentration of 0.30 over here. See, that's really the only thing that changes with these problems, okay? So then we're going to do our same thing here, minus x plus x plus x. You might actually like these. It makes it a little bit easier if it's a certain type of problem, I guess I should say. So 0.30 minus x, x, and 0.30 plus x.
What? Where do you go?
Well, I thought we had practice.
Yeah, I thought we had practice today.
We're having a
That's what Ben said. Ben said practice.
we're having a scheduling issue. Okay. You can just put those up on my desk then if you guys have to go. So once we have this set up, then basically you just have to do your Ka expression here. All right. So 1.8 times 10 to the negative fifth is equal to, and where this would normally be x times, or x squared on the top because we just have an x and an x here. Now we've got 0.30 plus x, 0.30 minus x. So this could get pretty nasty pretty quick, except we're going to make the simplifying assumption here for both of these. Okay, I'm going to assume that x is small enough that it doesn't matter if I add it to 0.3 or subtract it from 0.3. I said that backwards, but you know, add it to 0.3 or subtract it from 0.3. Okay, so we can just ignore the x on those two. All right, so we end up with 0.30 times x divided by 0.30, which is kind of nice, right? Because all we have to do here is just cancel these two out. And we've got our x. So x is equal to 1.8 times 10 to the negative fifth, okay? You guys are just all way too busy. You understand that, right? All right. So if that's our x, that's also our H plus value, right? So we take the negative log of that, and that will give us the pH of this solution. So the pH, take the negative log of, I need a calculator for that one. Can't do that in my head. 4.74. That's what I'm getting here. Okay, and that's the right number, sig figs, because we had 2 in our K and 2 in our concentrations. So we need 2 digits after the decimal point on the pH. Does that make sense? Now, if I had not dumped in the sodium acetate, do you think that pH would have been lower or higher? Probably would have been lower, right? Because what I did was I dumped in, again, some of the product, which pushed it back this way, lowered the H plus concentration, and made the pH higher than it would have been otherwise, okay? And you can actually do a quick calculation and figure out, all you'd have to do basically is change this calculation up here to an x squared at the top and a 0.3 at the bottom. Okay, and if you do that, you can figure out that the x would have been 3 times. The x would have been 0.0023 or something like that. That would have been your H plus concentration without putting in the sodium acetate. So then you take the negative log of that, and your pH is right around 2.64. Okay, So quite a bit lower if we didn't put the sodium acetate in. All right. This is very, very similar, okay? We're putting in nitrous acid and potassium nitrite. So I don't think I need to go through how to work all of these, but I think the setup is half the battle here, just knowing what equation to write when you're looking at something like this. So you've got the nitrous acid, and you've got potassium nitrite. So what's the common ion there? What's the ion that both of those are going to have in common? It's going to be the NO2 minus, right? The nitrite. So when you write your equilibrium expression here, I would just, again, start with the acid because they're asking for pH again, so I want an H plus concentration. Okay? And once you have your equilibrium, when you set up your ice table, then you've got your nitrous acid is 0.085. Your H plus is still 0 here to begin with. And then you've got a 0.10 molar concentration here. Now, this one's not going to work out as nice and neat as the other one where the numbers cancel out top and bottom, but you can still work it out pretty easily. You just make your simplifying assumption just like before. And then you should be able to go from there. That you guys feel okay about your ability to work that one out from there with the minus x's and the plus x's and all that stuff. I think the setup is just the hard part. Just remembering this is not going to be 0. This is going to be some concentration, however much of that we're dumping in. Okay, pH of the following: a solution made by combining 50 milliliters of 0.15 molar acetic acid and 50 milliliters. Okay, that's not much different. The only thing that they're adding there is a step where you have to realize that you are dumping two things together, right? So what does that do? 50 milliliters of one, 50 milliliters of the other. As soon as you dump them together, what does that do to the concentrations? Yes, that's right. What it will do is divide them in half, right? Because we're doubling the volume of the solution. So you can do an M1 V1 equals M2 V2 here if you want to for both of these. But I think probably most of you, once you hear it explained, it'll make sense to you that, okay, we're doubling the volume, right? Because we're adding 50 to 50. So this one was 0.15 molar in a 50 milliliter solution. It's going to be 0.6. Yeah, no. Bad mental math. 0.075? No. That's not right. That would be point. Why can't I do this all of a sudden? I'm sorry. This is really, yeah, 0.075. That was right. I just panicked. Okay. So 0.075 molar, right? And then the 0.2 molar will go down to 0.1 molar. So that's, I can do that one. Thank you. Thank you. No, I'm not. Okay, yeah, now I am. I had to make sure. Okay, so that's the only difference on that one. And once you have your new concentrations, then you should be able to figure everything out from there. Okay, that's the one thing that might trip you up on that one. Calculate the fluoride ion concentration and the pH of the solution. That is 0.2 molar in HF and 0.1 molar in HCl. Okay, this is a little different, so let's do this. What's the common ion this time? It's the H plus, right? It's every other example we've done. It's been the anion, but here it's not. It's the cation. All right. So I'm gonna write the HF equilibrium. Now, why am I doing that? Why am I writing the HF equilibrium as opposed to the HCl equilibrium? That's right, because there's no such thing as an HCl equilibrium because it's a strong acid, right? So that's not an equilibrium, so this is the only equilibrium that I can write here, okay? So then we're just going to kind of think about this in terms of the ice tables again. And I guess I also need to know the Ka for HF, which I forgot to put on this one. I don't know if this one's in the book or not, is it? I should have a book in front of me. Is it? Okay, do you see what the Ka is for that? Okay, thank you. All right, so there's our equilibrium expression. We've got 0.2 molar HF, and this time we've got 0.1 molar HCl. Now the Cl minus doesn't matter, right? That's not in our equation here anywhere. But the H plus does matter. So now instead of having 0 H plus to begin with, we actually have 0.1. That's weird. I don't know why that happened. And then we have 0 of the F minus to start with. Okay? So then same deal, minus X plus X plus X. X, 0.10 plus X, and 0.20 minus X. I don't know for sure if we can use a simplifying assumption on this one. I'm going to do it, and then we might have to check ourselves at the end to make sure, because that's a fairly high Ka value for a weak acid, but we'll see. All right, so then you plug all this in. 6.8 times 10 to the negative fourth is equal to 0.1 times X divided by 0.2. And then you just work all that out, and you should get your X value, which should be, I'm going to end up multiplying this by 2, aren't I? Yeah. So, whatever that is. It's really sad that I can't do that in my head. You guys need to learn from my mistakes, not use a calculator for everything in your life. Or do, you know, and then, no, it doesn't work on the AP exam, that's for sure. 0.0014 or so. Yeah, I don't know. I don't make the rules. If I did, this world would be a scary place, I think. So it's probably best that I don't. I don't know why I circled that. I think it's because I was trying to make a joke, and I got distracted. That's not the answer to our problem. The answer is the 0.1 plus this 0.0014. Actually, let's check our assumption and see if it was okay that we made it. 0.0014 divided by 0.1 times 100, 1.4%. All right, we're okay. And some of you are watching the video and being like, and he couldn't do that one in his head? Divided by 0.1 times 100? Yeah, should have been able to do that in my head. That one I wasn't even thinking about. All right, so our simplifying assumption, we're okay there. But that's our X value. That's not our H plus value, right? What's our H plus value to the correct number of significant figures? If I take 0.10 and I add to that my X, 0.0014, to the correct number of sig figs, the answer is 0.10. Well, what's the moral of that story? The moral is if you put a weak acid in a solution with a strong acid, guess which one is going to determine the pH of the solution? The strong acid, right? Okay? So it didn't matter that we had that 0.2 molar HF in there at all, really. The 0.1 molar HCl is what determined the pH of the solution. So we could have just taken the negative log of that 0.1 and figured out that our pH is 1. How many sig figs? 1.00. Why did it do that? It's weird. Okay. So then, very quickly here, ionization of a weak base does basically the same thing. Sorry. Calculate the pH and the trimethylammonium concentration of a solution that is 0.075 molar in trimethylamine and 0.10 molar in trimethylammonium chloride. That's interesting. So again, I think the hard part on this is just writing the initial equation, figuring out what is the equation that I actually need to write here to even get this thing started. Any ideas on this one? I see nitrogen here, so I'm probably thinking base on this one, maybe. And then I see a chloride at the end of this one. So this looks like a maybe an ionic compound. You guys see that, where maybe the chloride comes off? That's a little bit tough to see maybe, but that's what's going to happen here. Okay, so you've got CH3, NH. That's going to be positively charged because the chloride is going to have the negative charge, right? So now, can you kind of get an idea of what's happening, maybe? Maybe we've got this CH3 in water, and it takes the hydrogen from the water and becomes CH3 NH plus, and then we've got some OH minus. Okay. Although, maybe I want to write that the other way. Maybe I want to write that as the acid reaction because I'm trying to calculate the pH. So you can do it this way. You can figure out the OH minus concentration, take the negative log of that, then you'll have the POH, subtract that from 14, and that'll give you the pH, right? So that's totally fine. Kind of depends on whether they give you a Ka or a Kb on this one as to which direction I would go with it, because if they give you a Ka, then I would definitely write the acid reaction, because it would be much easier. If they give you the Kb, then it's kind of probably doesn't matter which way you do it. But the way you would write the acid, if we're thinking about this acting like an acid in solution, then the equilibrium would be CH3 NH plus in equilibrium with, I don't know what happened there. I just killed a Y or something. That's what it looks like. There we go. That's a little better. CH3 N plus H plus. Okay. So then if I use this equilibrium, plug my numbers in there, then I will get an H plus concentration for my X value, and then it's a little bit easier to calculate the pH. All right. But then your ice for this one, just to make sure we've got this. Trimethyl, let's see, 0.1 molar here, and then it would be 0.075 molar over here. I don't need that. And then we'd still have 0 of the H plus to start out with here, okay? So then you just work it through like any other problem that we've done so far, okay? But you could do it in terms of the base if you wanted to, or you could flip it and do it in terms of the acid, whichever one. All right, so that's it for today. Tomorrow, buffer solutions. Yeah, that'll be fun.